Yeah.
Good afternoon. Today I'm going to talk to you guys about applications of machine learning in the finance industry, or the shorter, maybe the same length title, how to use data science to solve business problems. So I have a background in particle physics, but I sold out after my master's at the U of A, and I quickly found out I could apply all of the problem solving techniques I learned in academia, and in this case physics, to other scenarios, whether it was government problems or financial problems. So to put everyone on an equal footing, I'll give you guys a really high level view of ATB Financial. So ATB is a crown corporation, which means it's owned by the province of Alberta, but we don't take direction from the government. So we have a mandate to provide banking services to all Albertans. And so we operate all throughout Alberta, but only in Alberta. And we have about 5,500 full-time employees and around $56 billion in assets or loans and equity. I'm going to close my window so that you guys don't have to hear my neighbors making noise here. So when we're talking about the reach of ATB Financial, it was started back in 1938 during the Great Depression. Essentially what happened is there was this big economic contraction, and the banks out east that were headquartered out east, they wouldn't give loans to Albertans, so struggling Albertan farmers and just the average Albertan. So the government took it upon themselves. They said, no, we are actually going to make our own financial institute and loan money and create liquidity for the people of Alberta so that we don't have to rely on these banks that are headquartered elsewhere. And over the years, the last 80 years or so, it has grown to provide services to Albertans in about 250 communities, so 173 branches and 140 agencies. We've grown that customer base to about 800,000. So when you consider there's a little over 4 million Albertans, this bank really does provide like a crucial banking service to Alberta as a province. And it's one of the few examples of a profitable private or publicly owned financial institute. So it's really, really neat. And a lot of people don't know that much about it. So what is the company structure? ATB is composed of a number of smaller business units with specialized roles. So everyday banking provides retail bank accounts. Those are the checkings and savings accounts that you or I might get for our personal use. But there's another group for business and agriculture banking. So they're more specific to small and medium businesses, farmers, startups, things of that nature. And then we have another group called ATB Wealth. These are your investment services. So if you're not looking for a checkings account or a savings account, you want some financial advice for long-term investments or registered retirement products, you'd go and you would talk with that division. And then finally, there's a technology, innovation, and engineering group. And you can think of this group as the technical infrastructure and the data services that kind of support the rest of the organization. And there's a whole bunch of other subgroups, but these are some really high level divisions of the company in terms of functional area for you to understand how all the pieces fit together. So within that last group, the technology and innovation and engineering group, we have this data and AI division. It used to be called the AI Guild. And this is a team of about 120 people. And we're responsible for using data and technology to make ATB more efficient and more profitable. And, we do that by making the customer experience better and providing better banking services to Albertans. So this is the part of the financial institute where you see data scientists, software engineers, product managers, quality analysts, database admins. These are people who tend to have a more technical background. And I put in quotations here that they're all working in harmony, because it's really challenging to get that business team to meet this kind of data science team and come together to solve customer problems, really, how we provide the best service possible to Albertans. And on the right-hand side, I've shown a couple like bigger groupings of work that we do in this division. So data science being a big one, automation is another one we do a lot of work in. Business intelligence, which is reporting, I would say, right? It's gathering the right data and getting it in the right hands of the right people at the right time. And then there's a renewed or a new heavy focus on AI governance and ethics. So making sure we're doing this safely and not, biasing our models in any way. So it's always good to start with a quote. And I think if you're at a company and you're trying to use data science to provide value, you need buy-in from the top. You need the people at the highest level to really, truly believe in the technology that you're bringing to the table. So this is a quote by our CEO or our president of ATB Financial from last year. He said, "We have an urgent opportunity in front of us as a province to lean into technology, AI, and data and use it as a growth engine for the province." And there's a number of other quotes that I've used in the past along a similar line. So this is kind of showing you that we actually do have buy-in for the top. And this is really, really important for being able to have the impact you want as a data scientist or someone who's trying to apply machine learning in a banking setting. Okay, so I'll give you like a smattering of different ways that I have seen machine learning applied to create value in banks or in the finance industry. And then I'm going to take a handful of these and go into a deeper dive on more specific examples. So the first thing we do is product and advice recommendation system. So you can think of this like your Netflix account, but for banking, right? When you come into the branch, you only want to be offered products or engaged with and given advice that is relevant to you. And so to do that, we need to build some kind of an engine that analyzes all of our data and brings that information to the customer. There are decision support tools. So in the bank, there are lots of decisions that have a high monetary impact, and they have to be done with as much kind of data backing them as possible. So machine learning ends up playing a big role here. Fraud detection is a big one, right? How do we look at all of the transactions we have and tease out which ones are nefarious or someone who's trying to abuse our system and game it? Automating loan servicing. So, banks take in deposits and then they loan out money to people, and you have to service those loans. So if you can automate as much of that process as possible, you're going to make a better experience for the customer and save you money on people who now no longer have to do manual tasks. They can spend their time with relationship building. I've seen it used for physical network optimization, so knowing where to put branches or ATMs, data remediation, information retrieval, which I'll get into, virtual assistants, and customer churn prevention models. So trying to tease out which customers are going to leave us and why before they actually do. So that's like a general smattering of different applications. And I will go into a couple of examples or use cases. So the first application, I've called it automated information retrieval, but it's really around how we service our margined loan accounts. So if you're a business in Alberta and you don't have a lot of physical assets, but you bring in a lot of money and a lot of money comes out, you have a high throughput. We have a special class of loan called margined loans. So we actually give a loan amount relative to your throughput, right? How much money you have kind of flowing through your company. This is called a margined loan. We have about 2,000 of these accounts and about $3 billion in authorized limits. So this is a good portion of our business loans. And to maintain all of these accounts, it's really, really time intensive. And there's lots of manual effort. So front of line staff are getting emailed documents. They're opening those documents and searching through them and grabbing out account numbers and names and balance sheet totals. And then they're putting that data into a back-end system. And by the time they get it finished for the month, the next month's data has already started rolling in. So we asked ourselves the question, how do we automate this task of opening a scanned document and extracting small bits of crucial information? That's the automated information retrieval problem at hand. And to give you guys an idea of what it actually looks like, the task in a nutshell is something like this. You're given a scanned document, and it's composed of a whole bunch of key value pairs. So something like this is the property address, that's the key. And you're saying, well, I want that person's property address. And so the value is next to it. Same with their file number. You need to go in there, and this is what the human does. They search for the key, and then they grab the value. They look at that pair, and they pull out the value, and they put it in a system. So we need to do this over and over and over, millions of times a month. And you can imagine if humans are doing this, this is not fun work. It's kind of boring and it takes a long time. So to start out solving this problem, the group who built this solution started with a page classifier. So they actually get a whole bunch of documents with different pages in them. And some pages are, these accounts receivable. This is a list of all of the other companies who owe you money, whereas accounts payable will be a list of the companies you owe money to. They also get balance sheets. They often get these big packages, and they need to know the same thing a human needs to know right off the bat, which page has the information I care about. So they actually built a classifier, a machine learning classifier that first extracts features from the page. It actually looks at the page, and then it breaks that page down into kind of what is on that page, what types of things are there, how does it look, right? Does it have, lots of horizontal lines versus vertical lines? Once you build, you extract the features, they use an ensemble model of a bunch of different machine learning classifiers to classify the pages. So they have a big training data set that's labeled, and they're at super high accuracy, like 96, 97% of classifying 40 or 50 different types of pages with very, very high accuracy, so that they can say, okay, given a big document with 30 pages, which 3 pages have the information I actually care about? So they have a very, very strong machine learning classifier. And one of the people who helped us build this classifier was actually another U of A grad, a postdoc in condensed matter, who was doing this for looking at the atomic surfaces of different materials. So it again just shows that transferability of machine learning. It can go right from one situation to another. It doesn't care as long as the problem is kind of similar. So now we've got the pages we care about, but it's important to note these aren't pages with embedded text. These are true like pictures of text. So the process by which we read off the text is called optical character recognition. And again, there's a ton of machine learning in the background here, where they look at a picture of a document and you're able to very, very accurately extract what those letters are. And if it's a typed document, you get extremely high accuracy, and you go from a picture to structured data, text data in a database that you can further process. There are times we get, a farmer has scribbled down exactly his head count of cattle. Okay, that gets flagged and brought off to a human to read. But for the majority, the documents that come in, they're able to classify them and extract the text out. So we use optical character recognition, or OCR. We pull out the text, and now we're trying to hunt down those key value pairs. So they apply another set of machine learning algorithms called named entity recognition. This is a type of natural language processing. But at the core, what it's doing is shown on the right-hand side here. So there's a sentence, and the NER, or named entity recognition algorithm, is actually reading the sentence just like a human would. And it is saying, this word, Trump, is a person, and this word, FBI, is an organization. And this word Monday is a date. It's actually learning the context of those paragraphs to say, okay, this is another grouping of what all of these words are. And once you've trained one of these NER taggers really, really well, you can get it down to the point where it knows what are account numbers versus addresses versus telephone numbers. It learns the structure of those values from the key value pairs. And it doesn't even have to be a key value pair now. It can actually pull it out of a sentence. And then once you say, okay, we saw 4 account numbers on this page, we check they all matched. That's probably the account number for this, accounts receivable table. And we saw this organization name, that's the business name. You can build in some checks after the fact, but you've reproduced through a series of different machine learning algorithms what a human is doing. You really are automating it and building a system that can replace the tedious task this human was doing. So that's a lot to go through. So I put up a solution stack overview. This is kind of a cartoon of what's happening. We start with those raw scanned documents as an input, and we go to the page classifier, and it pulls out some of the pages we don't care about, and it keeps the ones we do care about. Now we go to a step where there's a bit of computer vision. So we're cleaning up the scanned document. We're removing artifacts and we're sharpening the text to give the OCR algorithms the best chance possible of pulling out the text as well as where it appears on the page. So text in the bounding boxes, that's the optical character recognition. And then you actually extract just the text you want, just the information you care about. So you've gone from unstructured, messy data down to just the things you care about. And you can extract that, put it in a flat file. And the way they have automated it, this happens in under a second, whereas it used to take a human 10, 15 minutes to do. And then the robot that automates this in the background goes and updates that customer's loan amount almost instantly. So before they would wait a few weeks for a human to work through the backlog, and now they're getting it instantly, which means they have access to the money they need to run their business in a much shorter time. And that's leading to a better customer experience, which is the end goal. Okay, so why did we bother doing this? What was the return on investment? So there's near full automation of servicing of about $3 billion worth of this type of loan. This is freeing up around 6 staff, probably more, to instead of spend all their time doing a manual task, they're now doing the more important work, the relationship management, the stuff that the computer can't do, calling those businesses and asking them if they need extra help or extra financial advice. And so this saves hundreds of thousands of dollars, about 400,000 if we're being really, really careful. This is probably an underestimate is what I'm saying in the cost efficiency. And on top of that, we asked a number of companies, what would it cost to build this? And they said to even look at this problem, you're looking about $1 million. So now we have permanently saved that money and created a better customer experience. And on top of that, it wasn't just for one project. Like we started with one project, but this scales. So all of the OCR learnings, the named entity recognition tagger, the machine learning page classifier, the team that does this can really, really quickly spin up a new solution to a related similar problem. And the first time it might have taken 9 months to a year. And I heard recently they did a proof of concept in something like 2 to 4 weeks. So they just took all of the pieces and they refactored it. And they said, now we're solving a really, really similar problem in 1/10 of the time because we already put in the legwork and we just need to scan a different type of document and look for a different key value pair. So we're talking about huge ROI here, like in the order of millions of dollars saved with the ability to quickly scale that value much, much faster in the future. And for the cost is like hundreds of dollars per month for our cloud computing. And then there are the FTEs, the data scientists, that have to maintain it once it's running, but it's still much, much less than the original cost of providing this service to our customers. So this is a big win. This is a cool way to use machine learning and automation for banking. So the next application, I'm calling it risky behavior detection. And I'm not allowed to tell you what the behavior is because if it got back to the people who might be taking the risky behavior, they'd change their behavior and I'd have to update my model and I don't want to do that. So this is the business problem. We have a whole bunch of staff at ATB, and they're doing their best to follow all of the policies and procedures that the regulators say we need to follow to make sure we're doing this safely, right? We're not putting ATB under any undue risk. So as a staff, you have to follow certain regulations or certain policies that keep us in check. But every now and then you can unwittingly create regulatory risk if you're not adhering to policy. So maybe you forget a step here or there, and all of a sudden you didn't, cross all your T's and dot all of your I's in some process, and that opens us up to regulatory risk. So this can lead to fines. We really need to make sure this risk is always mitigated. So we always have to detect this behavior, and then we remedy it. We go and we educate the people and say, you forgot to do this step or that step. This will get us in trouble with the regulators. And you give them some training and you're away and going. You're kind of as clear as possible or as free as possible from this regulatory risk. So we were trying to detect this risky behavior, and there was so much work to do that they could only ever do a random sample and check on that. And they really wanted to see if they could use machine learning to look at all of these events that we might want to detect risky behavior in. So like any good research problem, it starts with data gathering. So I went and I collected a wide array of data sets from internal data stores and warehouses. And I said, okay, now I have to normalize them and join them all together by these types of events I was studying. So kind of get one data set, and I looked at all of the underlying distributions and characterized them and said, okay, which of these data sets do I really, really trust? Where do I think there's low systematic uncertainty so I can actually get meaningful insights or reflections of the behavior out of this data? And then I kind of started with one big, clean, trustworthy data set to move on to the next step, which is feature set creation. And so the way I did this is kind of the opposite of the way you would take on a Kaggle competition. I actually went to the business expert in this behavior, and I looked at a big list of raw pieces of data on the different events I was trying to detect. And I said, what are the telltale signs? How do you know? And they literally scanned through it and said, you can see something's weird right here because they took too long at this step. Or you can see something down here where they went back and forth to something too many times. So I listened to what the business told me they did to detect this type of behavior, what the flags were through their years of accumulated experience. And then I created a bunch of features that should be good predictors to classify those events. So I've shown what you end up with at the bottom here. You have a whole bunch of different events, and then you have your feature set of all of your different features, and then the class, where a 0 is a background event or noise. You don't care about that. And a 1 is a signal event. So this is something you do want to detect. This is an event where in the past they saw, yeah, this was risky behavior and we had to investigate it or whatever. And so the 1s are the things you're trying to detect, and the 0s are the things that are okay. You don't have to go and dig any further on those. And I built up a big training data set of about 500 or so events. And I said, okay, I've got fairly good balance of the number of signal events I want to the number of noise event. Like there wasn't really a high class imbalance here, which is a good start. And then I chunked out randomly 400 events and made sure I had a good proportion of signal events. And then I held out a test training set. So this is a single training or test split. And like everything in data science, you just import some sklearn packages and you're on your way here. And now that I have this data set for training, I tried a few different classifiers. So I tried a naive Bayes classifier. I tried a support vector machine, which is when you try and separate the events in some kind of a parameter space and then find a hyperplane that separates the signal events from the noise events. We also experimented with something called a relevance vector machine, which is like a support vector machine, but it uses kind of prototypical versions of those events. So actually the easier ones to classify, and then looks for ones that are close proximity to those. And as always, you end up using some kind of tree-based method. So I played as well with a random forest. So I ran them through these algorithms and said, okay, for this first test, given everything I knew about our tolerance for false positives and false negatives, I said, to start, accuracy is actually probably fine here. Like you can use any number of metrics when you're building a machine learning classifier if you know what you care about. And for this, I said, accuracy is fine. I looked at all of the classifiers and found a winner, the random forest. And the other important thing here is the support vector machine was pretty close. The naive Bayes wasn't that far behind. And the relevance vector machine, okay, didn't do as good as the rest of them. But what this showed is all of them did pretty well. Like compared to just like the trivial case of guessing all one answer and seeing that about 80 or 90% are actually already signal events. This is telling you that there's a clear separation between your signal and your noise in the feature space you've created. So this is telling you by trying a bunch of different algorithms that you are kind of on the right track. And then I said, okay, but I only did one random split, and that's not good enough for me. What if I just accidentally picked a really easy split of the data? And so I wanted to get a better idea of how this might perform in the future. And to do that, I did with basically a bootstrap. I went and I picked a whole bunch of different test training splits, trying to kind of maintain the same signal to noise ratio in each of them. And I ran that same experiment over and over and over where I tested the classifier's accuracy. And so at the end of the day, you get a distribution of accuracies, and you can tease out the mean as well as the standard deviation of these distributions, and you can get a better idea of how you think this would behave in the long run. And now you can see the naive Bayes. I must have just gotten lucky on that first split, because its mean was actually much lower than the means of, say, the support vector machine over repeated trials or the random forest. So based on this type of analysis, I said I'm probably going to go with the random forest. This gives me the best feeling about what's a strong performer. So in the end, I said, okay, the random forest is also good because it's easy to explain a tree-based method to the people on the other end who are consuming the insights. It had strong average performance. You can output variable importances, which actually helps you explain a little bit more about which of the features are the strongest predictors. And so really it's a good model to kind of explain to people who aren't machine learning experts what you kind of think the model is doing in the background. And something I want to stress here while checking to make sure I'm somewhat on time is the success of the classifiers is heavily predicated on the fact that the features were handcrafted to solve the problem. So I get a lot of people, especially right out of school, they just did a bunch of Kaggle competitions, or they have a nano degree, and they say, give me all your data, I'm going to run it through a neural net, and then it doesn't work, and they say, well, machine learning is a bad solution here. And I say, no, you gotta really think how a human would do this and build features like a human would do it, and then run that through the algorithms, because you're actually like giving the algorithm a better chance of teasing out those two events, the signal versus the noise, by telling it the story as clearly as possible, by aggregating the data just right and kind of distilling it. So it's not a case of I threw everything I could into a neural net and it just worked. It was far from it. So what were the results? We actually operationalized this model, and the team went from randomly sampling about 10% of the inputs to examining all of them with the classifier and then only looking at the most likely ones. And it increased their kind of workload, the team that looks into these events, by a factor of 10. And most importantly, like the proof that it works is the lift was about 5. So they looked at using their random sample, they had a certain rate where they found this many things they had to actually take corrective action on. But when they started using our machine learning classifier and organizing their work that way, they were 5 times more likely to find those events and kind of correct that action ahead of time. So this shows it works. This is like the equivalent to the lift of some kind of a marketing model. And it was one of the first examples of a fully built, fully deployed application of machine learning where a machine learning algorithm is the primary thing causing value. It's not just one thing in like a much, much bigger chain. So it was kind of cool to say, yeah, like machine learning can be used. And I've got the confusion matrix here, but I don't want to get into too many technical details. This is just something you look at that shows you the real label, what was actually noise and signal versus what the algorithm predicted as noise or signal. So you can kind of tease out how well it's doing at minimizing your false positives or your false negatives, if that's something you care about. So the third application, and I should be still okay for time, I'm hoping, is recommendation systems. So this is the business problem. The customers walk into a branch and the staff working there can't get access to all the data they need to engage those customers or recommend the right products. And even if they can access all of the data, it's hard to kind of boil that ocean of data to know exactly what to offer a customer or how to engage with them. So what does this happen when we have all of this data about our customers, but we don't know how to use it or get it to the people who need it in the right format at the right time? It leads to, customer churn, reduced customer satisfaction, reduced customer deposits, holdings. It also lowers like the overall financial knowledge about the customer if you're not able to give them the right information that they might need. And then overall customer lifetime value, which is how the bank measures profitability of a customer, given how much it costs to maintain their accounts versus how many fees we collect on them or interest. So this is the problem. And the tool that they built at ATB is called the Next Best Conversation. So I'll abbreviate this as NBC, but this is our Netflix style recommendation system for deepening relationships with our customers and improving the product holdings. So this is powered in the back end by sometimes business rules and sometimes machine learning, and it's used to spark these meaningful, timely, and relevant customers. There's nothing worse than you go into a branch and you already have a MasterCard or whatever, and they just offer you a MasterCard because that's the most profitable product for them. No, you really want the thing that's going to do the best for you at a given time in your life based on your current banking needs. So the NBC tool, this is our recommendation engine, attempts to engage these customers by saying, hey, you look like you're at a point in your banking journey where you might want to build credit, or hey, we noticed you're paying fees on this type of account. It's like a 10-year-old account. We can move you into another account, given your usage, that's going to save you money, or even celebrating key events. Hey, thank you for being with us for 5 years. And at the end of the day, too, we have to provide some product recommendations. So, hey, it looks like you've got too much in your savings. Would you like a tax-free savings account? We don't see that you have one on file or whatever. This is the general idea. And how do we do this? Well, we start off with, like everything else, the input data sources. So you need to preemptively predict a customer's needs and wants, kind of tease out who they are, what they do, and how they use your banking services. So we look at demographic data. What are the characteristics of the neighborhood they live in? What is their occupational data? Do we know what they do for work? Do we know what their income is and for how long they've worked there? What are their product holdings? What products do they already have with us? Account level data. So, what is their balance in their checking account versus their saving versus maybe their long-term investments? And then what does the transaction data look like? How often are they using our products? Are they always going online, or do they always go into a branch? We really need to know the customer. And at this point, we apply a lot of ethics and bias checklists. So we make sure we're not using data that's under a protected class. So we never say, put gender or race into a model. Like, this is a really great place where you sit down and say, the data I'm looking at is purely behavior based, and we're going to do our best to make sure we're not doing anything that's going to bias our models. Once you have the input data, you can engineer a few kind of curated data sets. So this is similar to what we did before. We're taking the raw data and we're looking for trends in the data, and we're highlighting those trends in one feature data set on our customers. So, if you transact 5 times a month versus 3 times a month, we might actually put you in one grouping of low transactions versus, 10 or 15 times a month. So you kind of refine the data a little bit. We calculate churn likelihood, lifetime value, segmentation. So we try and group customers. We look at sums of balances, trending behavior, and then we come up with 2 types of products. So engagement products we come up with 2 types of offers, I guess, engagement offers and product offers. So the engagement offers are for deepening relationships. The product offers are for giving them the right banking tools to suit their needs. And the first set of offers, the engagement offers, are often really simple rules-based triggers. So, we might wait for a customer to hit a certain threshold. They're getting close to the point where they might want to draw down their RRSPs. So we just set a flag that, hey, do you want to convert to the type of account that lets you draw down on that in a way that you don't get dinged on it in taxes? If their birthday's coming up, wish them a happy birthday. If you're doing in-branch transactions that could easily be moved online, we don't need machine learning to tell us this. We can just set some triggers in the data that generates a recommendation and says, hey, talk to the customer about this. And despite being simple, these engagement offers are still shown statistically to reduce churn. So it stops customers from leaving us for other banks and increase the customer profitability. And we do this by having a treatment and a control group. So we temporarily hold out some customers, not for eternity, but for a short period of time. And we don't give them an offer when we otherwise could have. And then we do treat customers with the tool. And so now we have a treatment and a control group, and we can look at the differences in their behavior over time. And so we can use this to say, look at something like, I'll call it profit, but we have like a very technical definition of economic profit over operating revenue. And so we can say, okay, before we applied a treatment to our treatment group, what was their economic profitability? And then 6 months later, what did it look like for the treatment versus control? So we can say, based on all of the data we have, and it's statistically relevant or significant, that saying happy birthday to a customer, on average, boosts their kind of economic profitability by $4 a month. That really leads to a better customer experience and more happiness. Same thing with saying thank you for banking with us. That has like a real quantifiable impact on the customer lifetime value. And then something like a product offer. GIC is a type of investment. It's a guaranteed investment certificate. It obviously has a higher economic profitability, even just making that offer to a person. So we can actually quantify the impact of our recommendation engine, even when we're not selling products, which is really, really important. The product recommendations, we do use a bit of machine learning in certain instances. And the way we do it is we try and target a customer given their current state. So it's important to know we're not looking just for a customer, but we're examining a customer at a certain point in their life or a certain place in their banking journey. And so you basically hold out, you look at a data set that says over this time window, these customers took a product in, these customers didn't, and now you can get your treatment and your signal and your background class, and then you can look at the next, say, 6 months, and you can say, okay, of those people in this next 6 months, who do we think was likely to uptake a product or not? And we can build a test training data set that way. And again, we've seen really, really strong lift, sometimes low, but sometimes very high, like on the orders of 7 or 8, meaning this technique over just a random sample does much, much better. It actually lands successfully for a product offer 7 or 8 times as often, which is important. And another thing that's important to note here is we're lucky. We're a bank with 83 years of data of customers being offered products and then either uptaking it or saying, no, sorry, not right now at another point. So the product recommendation engines, they're unique for every product type. So short-term savings versus medium or long-term, they'll all have slightly different uses for a person. And so you can't just put them all in one machine learning model. We really have to build them separately. And in general, we find logistic regressions and boosted decision trees seem to work best. The advanced models like a neural net, they take a lot longer to train and they don't always have a good boost in accuracy. So we don't often go down that route. And any lift we get over a random sample is deemed successful because here, we want to make sure that we're offering customers the right products that they need. And if you can do that many times more often versus just your random sample, then you're probably getting something useful from that data. It's not statistically likely that you're getting like an 800% boost or whatever. So I've got a couple minutes left and I'll wrap up with the value creation of this recommendation engine, this kind of Netflix for our customer relationships. So we can measure the churn probability of the treatment and the control group and look at the churn probability over time, and we can see that it statistically reduces the churn of the customer. So it actually keeps them with us longer by giving them the right engagement and the right product offers. We notice it boosts customer profitability, which is again from a better customer experience and successful product recommendations. We can measure exactly what the product uptake rate is and what conversion rates are. So when we make an offer, how many times does the customer say yes, no, or maybe? And in about 4 years of operations, we've made 1.5 million offers to our customers. And that's about 1,000 different conversations. So in one conversation, you might have more than one offer, right? You say, thank you for banking with us. And you also end up making a product offer. And we get about 70,000 to 80,000 uses per month. So it's not just for customers walking into a branch, but if you're a front of line team member and you're preparing for a call you have coming up, it's really nice to have this tool to say, hey, this is a snapshot of the customer and where they're at in the banking journey. This is how we might engage with them, and then use that before you even get on the phone and call them. Of all of those 800,000 customers for retail ATB has, about 50% of them have been impacted by at least one recommendation. So the kind of impact of this tool is actually really huge when you think about it over a 4-year time period. And then when we look at the ROI, so what are the economic benefits versus the cost of the teams to run the tool? The ROI is somewhere on the order of 6 times to 8 times annually, being conservative. So this is a real clear winner. If I'm stuck in the elevator with our CEO and he says, why do we pay data scientists at ATB? I say, because we make you 6 to 8 times more money than you pay us. And then he says, good, get back to work. And my data science team is happy. They get to keep working on cool problems. So this is my very sparse summary slide. Machine learning in finance. It works, it creates value, and it saves money, but only when it's successfully applied and the results are measured. If you build the coolest tool in the world powered by machine learning and you apply it and you change people's behavior or that you make their experience better, but you don't measure it, you might as well have not done it at all, because you need to get out there and tell that story so that people realize the value of data science in whatever industry you're in, whether it's resource economics or banking or government or oil and gas. So I hope I stayed more or less on time. It looks like 40 minutes. Thank you guys for listening. I had a lot of fun talking about this, so I hope you had a lot of fun listening. It's really hard presenting from your own room and you're on a Zoom call and you can't see if people are sleeping or eating pizza in the background of the colloquium. So with that, thanks, and I'll gladly answer any questions you may have.
Thank you, Rhys. That was a nice talk. I'm sure there are questions. So if you want to ask a question, just unmute. And Dennis?
Oh, can you hear me?
Yep.
Yeah, so I saw that like earlier, I think it was in the second slide. So you used like a lot of like supervised learning techniques. And so I was just wondering kind of like where, if at all, you use like a lot of unsupervised learning techniques.
Yeah, so quite often when you have a training set and you know ahead of time what you're looking for, supervised is the way to go. Where we use unsupervised learning is we've used it a bit in the physical network optimization and even a little bit in customer segmentation. So we might say, hey, we know these customers have to be grouped differently based on their behavior, but we don't know exactly what yet. You end up using unsupervised techniques for clustering, I guess is the answer to your question. So anytime we want to cluster our customers, based on their demographics and their banking behaviors, and we want to have about 10 clusters, you can specify it ahead of time. Then you can go and see the model will tell you if there really are close to that number of clusters of customers. And then similarly for when we're doing like network optimization, you can look at how many banks we have in some area and use some unsupervised techniques to see if there are good places to put a bank given how different businesses are clustering. So we use it for location optimization. And anytime you want to kind of group either your customers or your services or your physical locations, but you don't know ahead of time what the groups actually look like. So did that answer your question, DJ Gray? Thanks, man.
Any other questions?
I do. Can I ask?
Absolutely.
Okay, so Harry's very nice talk. I really enjoyed it. I have two kind of related questions. So for the first classifier application that you described, I understand that there is continuously data coming in every day or every month for that application. And are the training data sets updated month by month or day by day? And do you see improvements in accuracy because of the additional information coming in?
Yeah, thank you, Sandeep. So you're correct. We do retrain the models periodically because you have to analyze the classifier to make sure that something weird didn't happen with your inputs, right? So if all of a sudden they start sending you different document types, your classifier that was trained to recognize certain document types is going to go out to lunch. It no longer recognizes the pages because the input data is too different from the training data. So the team that manages this tool does periodically update and kind of monitor the accuracy. And they can see like there's a threshold for like success. And if that threshold, all of a sudden starts spitting out a whole bunch of documents that need to go to manual remediation or humans, then something's kind of broken in your chain. And the other thing I'll say is once they built a good classifier, they found that they could get a new batch of data that is unlabeled and they could apply the classifier. And when there was low accuracy in the classifier, they could go and tease out, okay, it classified this one wrong. But right off the bat, they now have a labeled data set that they can just check. They can manually check and say, this page is right, this page is right, this page is wrong, this page is right. So all of a sudden they have like they're supercharging their ability to build bigger and bigger labeled data sets. And the more they do that, the better the classifier accuracy on individual classes, and the more classes they can accurately classify. I'm saying it too often, but
no,
imagine that they.
That's very clear. You're being very clear in answering my question. It's you cannot see my facial expressions, but yeah, that's exactly what I want to hear. So it does matter. And my second question is that your application about the risky behavior detection problem.
Mm-hmm.
You're sorting through a lot of information when you start the problem, but when you're training and validating, you have n is equal to 400. Do you have any concerns if that is enough for doing the type of training you're trying to do, like you're training based on the features to detect, let's say, I understand the features as me sort of every time I cheat in poker, I scratch my nose. So scratching my nose is the feature and the outcome of cheating, right? So is 400 enough? And can you talk about your own personal views about the sample size for training these kinds of data sets?
Yeah, absolutely. So like any data scientist, at the time I built that, I said, I need as much data as possible. I need like 10 million data points, and they need to have really like clear separation in the classes. And you get only what some people will scrape together in their spare time to help you. So I was worried about the sample size. The first indication that it was working okay was a relatively high accuracy. And I was actually able to crop out some of the features and pare it down to the smallest possible feature set while still maintaining a high accuracy. And I said, okay, well, a high accuracy is fine. It doesn't look like I'm overfitting. The real test will be if I use this classifier and give it to the people who are investigating and they say, no, you did worse. Like this is worse than just our random sample. Then I would have known that I didn't actually have clear separation between the signal class and the noise class in that feature set I had created. So the fact that they went and they investigated and they got a lift of about 5 or 6 told me that, hey, this is actually doing a good job of teasing that out, because they were detecting 5 times or 6 times more events than just from their random sample. So the proof is really in the pudding, I guess. It's in that feedback of them using it and saying, hey, this actually works. This is actually bumping our workload and making our jobs easier, and we're covering a greater ground. So that's how I was able to get the confirmation that the model works. And of course, it needs to be continually updated. And I guess like you asked my opinions on sample size. It really depends on the class balance and the class separability in the feature set or the feature space you create, right? Like when I say feature space, that's a fancy way of saying I lined up all of those columns and it creates like an n-dimensional space where you're hoping that if you plotted that on some kind of a higher dimensional graph, your signal and your noise would really clearly be set apart by some distance. That's what we're trying to do. So if there's low signal to noise and those feature or those signal and noise are really, really overlapped in your feature space, the biggest data set in the world isn't going to help you out. But if you have really strong separability in your feature space and you have at least a decent amount of examples, something like hundreds of examples can still be used to build a strong classifier. Now, like the closer those two classes get together in your feature space, the more and more data you need, and sometimes the more complex you have to build your algorithms. But it's less about the sample size and more about the class balance, so the signal to noise, and the separability in whatever feature set you're creating. And that's why sometimes people start with a machine learning model, it doesn't work, and they just keep adding features, and eventually they get enough of a clear lens on those two events that all of a sudden their class accuracy or their recall or whatever metric they're using improves to the point where it's worth deploying.
Very interesting. Yeah, it does. Very, very interesting. Thank you.
You're welcome.
Do you have a question? Catalina? I think you had a question.
Catalina actually put her question in the chat box. I don't know, Rhys, maybe you can have a quick look there.
Okay, how do I see it? I pop up this little chat window?
Yes, if you pop that up, they'll appear in there.
Okay, I can see the chat window, but ironically, it's like covered by this. Okay. I don't see the...
Oh, sorry, I didn't have my microphone on. I was listening on my speakers. Sorry about that. Okay, my question is, how do you think AI may be most helpful in collecting, storing, and cleaning up data, or in actual doing a statistical analysis?
Your first question was, how is AI potentially useful in collecting and cleaning up data? Is that right?
No, like what my question is, what do you think AI is more helpful in collecting and cleaning all that data, or in actually doing a statistical analysis?
I guess it's useful in both, but in different ways, and that's kind of cheating. But like like when we're doing that statistical analysis and measuring someone's product uptake propensity, we get some kind of an overall economic boost in the many millions. That's the order of magnitude. So that was the statistical analysis part. Now, when you're using AI and machine learning to clean up the data sets, data remediation or automation, if you use a lot of paper and your data is really messy, you actually end up with, again, like economic profitability in the millions of dollars. Like that's the return on investment. So you can see they actually have a similar scale, but that totally depends on the application. So if I went to another place that couldn't sell products, another company, but they were just drowning in paper or scanned documents, I might say, hey, you guys are spending all of your time doing this data remediation and manual processes. The lift would be way bigger there because the size of the problem in that company would be bigger. So it really depends on the size of the problem. And you'll see a lot of talk about AI algorithms being used in law now for doing like case studies and detecting exactly the right previous examples of trials and what their results were for very specific scenarios. And it's kind of upending the law industry and the legal industry because they just typically used to deal with like combing through large quantities of unstructured data. So they're like that type of information retrieval would be huge, but they're not selling products. So the statistical analysis part would probably be smaller. So I hope that gave you more context to my answer of it really depends on the size of the whale or the problem you're tackling, I guess.
Can I ask a general question? And maybe both Rhys for you and Lianhua. Here's some advice. What should we be doing as instructors to make sure our grad students are ready for this, what you're describing is a pretty exciting world? Or maybe what should the students also be looking for so that they can be prepared to move into this world? I mean, we're doing maybe traditional statistics. There's Sandeep does some machine learning and some big data analysis, but what kind of advice would you give us?
Leanne, I want to give you a chance to talk. So Leanne works with me closely. She's on my team and she worked with Vic, right? Dr. Adam Owitz. I don't want to butcher the last name. So Leanne, I'll let you take a shot at this and then I'll answer as well.
Thanks, Rhys. Thanks, Vic, for asking this question. And I just want to quickly say hi to all the students here because I'm so honored to be in this seminar. I have been in Vic's class 7 years ago, or 7 or 8 years ago. And then I really enjoyed Vic is teaching us about transportation models and random utility framework. I mentioned that because those stuff we have learned in grad school actually is very useful and relevant to those machine learning. Even though it looks different, the underlying problem solving techniques or the thinking process actually is very similar. And I benefit a lot from learning laying those foundations from random utility network and understanding CV, etc., those basics. So that's just my opening comments on this. So back to Vic's question, I think for from a student's perspective, maybe the first thing I would say is learn Python. When I was in grad school, I didn't learn Python, and my basic tool for stats analysis is R and MATLAB and even Gauss. Those are the old software. Right now, if you go to this machine learning world, it's all Python. Python is a must learn for grad school. I think if you're interested in those machine learning business, and that's my number one suggestion. And number two is about just to understand broadly about the application of various problems of machine learning. Rhys have given a very good examples, some very good use cases, and there are tons out there in different industries. And when you look at those examples and when you look at those use cases and think about, just to put yourself in that shoes and think yourself as a problem solver, how are you going to approach those problems? Just practice your mind and train yourself to try to think in machine learning way, if I can put that way. So that's my second suggestion, just broaden your horizon and then try to equip or train yourself with lots of real use cases. And the third one I would say is about big data. I'm not sure how you guys understand big data, but my understanding of big data is very different from when I was a grad student and then when I went to work in banking industry. These past, I would say, 5 to 6 years, this big data industries have evolved a lot. And right now, the Google Cloud platform is the platforming our company is using. And there are other cloud platforms as well. And those, everything is geared, I would say, about the scalability of the modeling, training, etc. So just to familiar yourself a little bit more about what big data is, what cloud computing is. So those are my 3 suggestions. I will give it back to you, Rhys. You must have more. Thanks.
I have a follow-up, Philip.
Yeah, go ahead.
Lianhua, I have a question for you, and it's admittedly a very naive question, and I think it goes back to Catalina's categorization of machine learning as things you do to clean the data and things you do to analyze the data, right? So my naive question is, when I'm thinking about machine learning or my students getting into machine learning, it's at the low end. They don't have a computer science degree, so they would have some basic skills in it, right? So what I notice is that R is, you said you used R is very proficient in machine learning algorithms. So when you talk about Python, which I've never used, I'm wondering what is the difference? Is it that if you know Python, then you can do more of Catalina's first point, that is cleaning the data? So you have more, it tells you how to scrape information, read things off a form that is handwritten, that kind of stuff. What is the difference between R and Python in terms of these machine learning skills?
So R is more of like a targeted language that grew out of like a bunch of statistical analysis packages. So Python is a general purpose language. And so they can do the same things when it comes to machine learning. But say you build a machine learning algorithm in R and the same one in Python. Now, when you go to deploy this in some kind of a bigger stack or a tool, it's a little bit easier for the Python deployment because it's a general purpose language, and it's a little bit harder for R. So for you guys, the academics or the students, like Leanne said, learn Python. And I would say, learn R, learn Python, learn whatever you want. Focus on the techniques and not the tool, because I started learning programming in a C++ object-oriented framework designed for particle physics. And then I moved to R and I did all my statistical analysis there. And then I went and I taught myself Python. And like once I learned the first language, I was able to just learn the syntax of the other languages. Once I knew what I was trying to do, what the techniques were. The tools are less important. But in terms of R versus Python, they're both good for just doing like machine learning analysis, but Python's a little bit easier to deploy in some kind of a software stack or tool. And that's why, they're both very popular machine learning languages, but Python's easier when you're in a company and you're trying to build it to then get plugged into a bigger stack, I guess. Did that answer your question, Sandy?
Yes, it did. Thank you very much.
You're welcome. And Leanne killed it. Like, I'll probably only just summarize what she said. For the teachers, focus on the techniques and the programming and the problem solving skill sets, and focus on how you might apply what you've learned. Like, usually as a teacher, you're trying to teach them so many different theories that you don't stop and say, hey, this is when someone took this theory and did something really awesome with it. So again, like my fundamental knowledge was in separating the different types of particle decay events for different types of whatever, electrons versus muons versus taus. Someone probably was thinking, well, that would never apply to finance. That guy knows stuff about particle physics. But no, man, I went into finance and I said, this is a classification problem at its heart, and I'm going to use the exact same particle identification techniques or clustering, but I'm clustering people instead of particles. And so it just transfers over, but you have to know how to apply what you've learned. You can't just say, well, I know this fact, but I can't take any action based on it. So that's like, for the teachers, kind of learn how to show applications whenever possible. And for the students, you got to know how to market yourself and how to network. So learn those soft skills, because when you leave academia, if you decide you want to, you need to learn how to network. You need to learn how to tell a story. And you need to learn how to showcase your skills and the things you can do, because you're going to get job descriptions that say you need 5+ years of experience in XYZ tool, but you might just be able to get an interview and say, hey, no, I can use whatever tool you want. Tell me what problems you have, and I'll try and solve them, I guess. So I hope that was okay feedback for both the teachers and the students there.
Thank you, Rhys.
Great.
You're welcome.
I think we about done in terms of time. We could take a last short question if there was one. If there's none, then thank you very much, Rhys. Everyone has to clap.
Thanks so much for having me. I really appreciate the chance to speak.